Dear students, today we are going to have a new session in physics and the topic is electrodynamics. Electrodynamics is considered to be the most royal topic in physics. In electrodynamics, we will be dealing with electrostatics, magnetostatics, then we will be dealing with electrodynamics, which means dynamic electricity. In electrostatics and magnetostatics, we will be dealing with static electricity and static magnetism. We have other sections also like applications of all these things. But today, I will be handling the first topic, which is electrostatics. In electrostatics, we will be dealing with static electricity. Static electricity means basically the electricity is due to charges. There are two types of charges, positive charge and negative charge. In that positive and the basic charge is having a value 1.6 into 10 raised to minus 19 coulomb, which can be positive or negative. And in static electricity, the charges will be stationary. And around that stationary charges, there will be a field. And these charges can exert force on, a positive charge can exert a force on a negative charge, a positive charge can exert a force on a positive charge, and if they are like charges, they will be having a repulsive force, and if they are unlike charges, they will be having an attractive force. Therefore, force is something that is acting between the two charges. But if that second charge is absent, there will be something around the first charge which will be responsible for the force. And that something around the charge, we call it as the electric field. In our first chapter, we will be dealing with electric field. Therefore, my first chapter is electric field. In electric field, we will be only dealing with the electric field only. In this chapter, we will be dealing only with the electric field. And basically, that this type of or this chapter is basically an ideal concept. We will be dealing with ideal concepts. Ideal concepts means actually we will not be able to put a charge somewhere and then measure that field. We will be doing everything in a theoretical way or a mathematical way. We will be defining equations, we will be getting the values for the electric field, we will be picturizing the electric field. All these things we will be doing in an ideal fashion, not related with the practical things. The first thing that I am going to do is I am going to define what is an electric field. An electric field, you can say, it is a vector field. It is a vector field surrounding an electric charge that exerts force on other charges, attracting or repelling them. And mathematically, the electric field is a vector field that associates to each point in space on the force called the Coulomb force that would be experienced per unit of charge by an infinitesimal test charge at that point. The units of the electric field in the SI system is Newton per Coulomb. For electrostatics, the concept of electric field is a convenient but not really necessary. Actually, this electric field concept in electrostatics is really a convenient way of representing the force, but it is not really necessary. Actually, we will be dealing with the practical cases only when we deal with electrodynamics. Electric field is an elegant way of representing characterizing the electrical environment of a system of charges. The true physical significance of the concept of electric field, however, emerges only when we go beyond electrostatics and deal with the time-dependent electromagnetic phenomena. And before going to get an equation for the electric field, first I will define what is the force between two charges. The force between the two charges was given by F equal to, therefore, the Coulomb's law, I can write in a scalar form like this, K into Q1, Q2 divided by R square. And explicitly writing that K, I can write that as 1 by 4 pi epsilon 0 Q1 Q2 divided by R square, where Q1 is one charge separated by a distance R from another charge. I can replace this by capital Q and small q. I can have any symbols I can use. R is the separation distance, and epsilon 0 is called as the permittivity of free space or vacuum, and that value of the epsilon 0 is given by 8.85 into 10 raised to minus 12 Newton meter square per Coulomb square. Therefore, this is the force between two charges, any two charges separated by distance. I am not considering what is the sign of the charges. If both have the same sign, either positive or negative, they will be having a repulsive force. They will be having a repulsive force, and if one is positive and the other is negative, they will be having an attractive force. And in vectorial form, I will be able to rewrite this expression as, if the separation distance and the direction is given by unit vector r, the vector force I can write it as 1 by 4 pi epsilon 0 q1 q2 divided by r square into unit vector r. Therefore, this is what is given by Coulomb's law. Remember, it is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. Inversely proportional to the square of the distance between them. My aim is to define electric field. This has been already defined. My aim is, this chapter deals only with the electric field, and it's how to picturize the electric field, how to quantify the electric field. Now, my first aim is to define the electric field. Therefore, if I want to define the electric field, I have only one charge. I have to consider only one charge. For example, if I have a charge Q here, I want to find out what is the electric field around this charge Q. How can I define that, or how can I mathematically express that electric field? For that, what I am doing is, I am going to write this. First of all, let me forget about the vector. I will write this equation as Q, capital Q divided by 4 pi epsilon 0 r square. This is my Coulomb's law. Now, I will take this Q to my left hand side. Then my equation now becomes F divided by Q is equal to Q divided by 4 pi epsilon 0 r square. 4 pi epsilon 0 r square. Now, I have one charge Q here and another charge Q here. I am finding out what I have is the force exerted by this Q on small q, or the force exerted by capital Q, so small q on capital Q. My aim is to find out what is the electric field, or some property which only depends upon this Q. I do not want both that is the interaction between this capital Q and small q. I want a property which only depends upon the parameters of this capital Q. And now my right hand side contains only the parameters that is related with the Q. If I have a charge here, I am finding out what is a property at a distance r from this capital Q. Therefore, that can be very easily obtained from the Coulomb's law. From the Coulomb's law, if I take that charge Q to my left hand side, I will get a property that contains only the parameters related with my first charge. Therefore, this property I will call it as the electric field. This property is called as, or actually this is the equation for that electric field. And to be more precise, but the point that you have to consider is that if I am measuring the field field of a charge, then if this is the equation, I have to take into consideration that this will not affect this capital Q. The field of this small q will not affect this capital Q. That has to be guaranteed. And to guarantee that, I will say that this is only a test charge, and that test charge means the charge on that small q is negligibly small. Or I will to make the definition clear, I will have a limit. I will say that limit q is tending to 0. 0 means it is a minimum charge. You cannot make q equal to 0. The minimum charge that we will be having is 1.6 into 10 raised to minus 19. And this capital Q will be the large number of charges. You can say that n into e. It will be an integral multiple of the basic charge. And this, if this n is very large, you can have this capital Q. And this test charge must be in such a way that contains only minimum number of charges. Therefore, our definition of the electric field now becomes, basically the electric field definition is now E in vector form. I can say that it is limit q tending to 0 F divided by Q, force divided by Q. Therefore, this has to be, whenever you define the electric field, this must be guaranteed. Therefore, let us forget about that and we assume that always this will be satisfied. Therefore, I can say that E is equal to F divided by Q, or F is equal to QE. F is equal to QE. F is equal to QE. Hence, we can say that F is equal to QE. And this provides one more definition for the electric field. This equation provides one more definition for the electric field. Looking into this equation, we can say that electric field will be equal to the force if Q is equal to 1. Therefore, if the force acting on one charge, force acting on a charge, if it is, the electric field can be defined as the force acting on an unit charge. The force acting on by a charge on a unit charge can also be considered to be a definition for the electric field. F is equal to QE, and if Q is equal to 1, then E will be equal to F, or electric field can be defined to be the force acting on an unit charge. Now, therefore, this is how we can define the electric field. Our aim is to define the electric field. Next one is to visualize the electric field, and third one is to quantify the electric field. What is electric field due to a point charge? What is electric field due to different types of charge distribution? And to have a visualization of the electric field, different scientists had given different methods for visualizing, and the accepted one is to draw the lines around the charge. The lines around the charge. We will assume that this is only an assumption. This is only an assumption that this visualization is based on an assumption that all the lines from a positive charge will be emerging from the positive charge, and for a negative charge, all the lines will be converging on the negative charge. Therefore, this is the convention. This is the convention that we follow now. From the positive charge, the lines of forces or the electric field will be emerging, and on the negative charge, the lines will be converging. Therefore, if you have a dipole, a positive and a negative charge separated by a small distance is called as a dipole. Therefore, on a dipole, we will be able to see that the lines will be, therefore, you have a positive charge here, you have a negative charge here, I will write here. Positive charge here, negative charge here, separated by a small distance. Therefore, the lines will be emerging from the positive charge and it will be moving towards the negative charge. If another charge emerges from something like this, then this negative charge will be attracting that line. Therefore, what happens is that it will be curving and ending on it. Curving and ending on it. Similarly, you have a positive charge from here also. Therefore, if it is like this or if it is like this, it will be going up because the other lines will be, these are all the positive lines emerging from the positive charge. Therefore, this line and this line will be repelling each other. They will be containing the concept of the positive charger or the idea of the positive charger. Those two lines, nearby lines, they will be repelling each other, and that repulsion will result in a line something like this. This has to end, this positive charge has to end on a negative charge. Therefore, it will be moving like this. It will be moving like this. If you have a positive and a negative, positive and a positive charge, then this positive charge field lines, if it moves towards the positive charge, it will be repelling. Therefore, the line will be moving like this. You have a positive charge line here. This will be similar, will be in the case of a negative charge. If I have a negative charge and a negative charge, the lines will be converging on the negative charge. But they will not be moving towards each other. They will not be moving towards each other. These are the pictures of the lines of force between positive and negative charge and a positive and a positive charge. Now, if you have a negative charge and a positive charge, they are not equal in size, equal in magnitude. Therefore, if I have a negative charge here, which is only 1 minus q, now you have plus 2q. The plus 2q means 2 charges are there. Therefore, when you can see that the charges will be coming from the positive charge, and the number of field lines near the positive charge will be greater compared to the lines near the negative charge. That has to be represented, since this charge has got greater magnitude than this one. Therefore, the number of lines, here the number of lines, you can see that only 3 is there coming and falling upon here on the upper side. Now, you can see that the number of lines is more compared to the number of lines here. This number of lines represent the intensity of the field, the number of lines. Therefore, more charges means more lines will be there around the charges. They gives the number of lines. This is the way of representing the electric field. Therefore, more lines gives you more intensity of the electric field. Now, when you are going to study about the electric field, or if you want to quantify the electric field, what I have given is discrete charges. But in reality, your charge distribution will not be discrete in 1, 2, 3 charges, etc. You will be having infinite number of charges, and they will be distributed in a region. They will be distributed in a region, and that distribution can be mainly 3 types. One is a linear distribution, the second one is a surface distribution, and the third one is a volume distribution. These are the different types of distributions which are not discrete, but they are continuous. There will not be, you cannot say that there is a space between the charges. They will be distributed continuously, so that there is no space between the charges. This is the way in which the charges will be distributed. And if I want to quantify the electric field, this is the real situation. Therefore, I have to first define, I have to find the way in which this continuous distribution of charges is represented by equations. For that, these are the different types of charge distributions, and they will have different geometries also. These charge distributions have different geometries also. They can be line charge distribution, they can be a cylindrical charge distribution, surface charge distribution, some cubical distribution, spherical distributions, etc. These are the ways. If it is only distributed on the surface, it will be a surface charge distribution. This is a volume charge distribution. And even in the case of a cylinder, you can have only, if it is a metallic cylinder, you will shortly see that there will be only a surface charge distribution. Therefore, to have more concepts about the electric field, I will be first making the idea of the continuous charge distribution. I will be mathematically expressing this charge distribution. The first one is, I will be considering a linear charge distribution. In a linear charge distribution, I will be taking charge distribution something like this. I can have a line. It can be a straight line, it can be a line like this. When I say a line, actually I am not drawing a line and putting the charges upon it. The charges will be distributed in the form of a line, not drawing a line and putting, or having a line of some rope or something like that and putting on charges on that. This is not the way in which you imagine a line charge distribution. What I have is a charge distribution. This is a really ideal case. I will be considering a charge distribution which is in the form of a line. In the form of a line. Therefore, it can be a straight line. It can be have a curve like this. But in electrostatics, I will be dealing, initially I will be dealing only with uniform charge distribution. You can have non-uniform charge distribution also, but initially we will be studying only uniform charge distribution. How will you define the uniform charge distribution? If I represent the charge density by lambda, then if I take a small piece, something like having a length dl, and if the charge on that length is dq, then my charge dq divided by dl, I will call it as the linear charge density. I will call it as the linear charge density, dq divided by dl. And if I want this, therefore, if I want my charge q, what I have to do is I have to take dq is equal to lambda dl, and if I want q, I have to integrate this. I will get q is equal to lambda dl. Therefore, this is the equation for a linear distribution of charges. The charge is distributed in the form of a line, and the linear charge density I will be representing by a symbol lambda. Now, I can have a surface charge distribution. I can have a surface something like this. I can have an arbitrary surface something like this. Then I have charges distributed on the surface. And in this case, my dq will be, I will be defining the charge density by the letter symbol sigma. Then my dq will be equal to sigma will be equal to area I will represent by the letter S. Therefore, charge divided by small area. Therefore, dq will be equal to sigma ds, and my q will be equal to integral sigma ds, where sigma is the surface charge density. There is one more charge distribution which we will call it as the volume charge distribution. It can be in a volume. Like this, and in the volume I can have in that case I will represent by the charge density by rho, that is dq divided by the volume dV. Elemental charge divided by elemental volume, then dq will be equal to rho dV, or q will be equal to integral rho dV. Therefore, there are three types of charge distribution: linear charge distribution with the linear charge density, surface charge distribution with the surface charge density, and the volume charge distribution with the volume charge density rho. Therefore, these are the three types of charge densities: dq divided by dV, and this can be represented as q equal to lambda dl or dr, or you can have the sigma ds, and q is equal to rho dV. Now, this are the definitions for the charges which are having different types of distribution. Now, you can have, my aim is to define or quantify the electric field. Before quantifying the electric field, we will be defining another quantity which is called as the electric flux. We define a quantity which is called as the electric flux. Basically, you can say that electric field can be, actually the flux means the number of lines. The number of lines around, the number of lines in any fashion, the number of lines around a positive charge, or number of lines between some positive charge and a negative charged plates. That number of lines, you can define that, or you can represent the electric field as flux number of lines per unit area. Or you can say that, or you can define the flux as electric field into area. Therefore, flux is nothing but the number of lines around a charge distribution. And that flux number of lines per unit area, you will be able to define the electric field. This is a way of defining the electric field. The number of lines crossing an unit area, you can call it as the electric field. And mathematically, you can write that electric field as phi divided by area, or phi is equal to E into A. But this means that electric field E is a constant and area is a constant. But that may not be the case, because you can have any arbitrary type of surface. Area means if you have a spherical surface, you can consider an area something like this. If you have a cylindrical surface, you can have an area something like this, a small area like this. But the surface can be any arbitrary shaped surface. Therefore, this small elemental area will also have an arbitrary surface, and the electric field also need not be a constant one. In that case, I will have to represent this phi not as two constants. I will be representing that phi as an integral of this electric field into an elemental surface. This is basically a definition. The flux phi, I will say it is a closed integral E dot ds. Closed integral E dot ds. And based upon this definition, a very famous law has been defined by the great mathematician Gauss. He said that the flux around a charge, or flux around a charge distribution, can be represented as that flux is equal to Q divided by epsilon 0, where Q is the net charge. Q is the net charge. What do you mean by net charge? If you have a positive charge, one positive charge and another charge, the net charge will be 2 plus. If you have two negative charges, the net charge will be 2 minus. But if you have a positive charge and a negative charge, the net charge will be equal to 0. Therefore, the flux around a positive and a negative charge will be equal to 0. The flux around a two positive charge will be equal to 2. If you have, this will be around a two charges will be equal to 2E divided by epsilon 0. Around the two negative charges, it will be equal to minus 2E divided by epsilon 0. Therefore, this is basically an equation that was put forwarded by Gauss. He said that the flux around any charge distribution will be given by Q divided by epsilon 0. Q divided by epsilon 0. And this is the definition of Gauss's law, and that we had defined that flux as closed integral E dot ds is flux as E dot ds. Therefore, E dot ds will be equal to Q divided by epsilon 0. This is the equation for Gauss's law. Using this equation, you will be able to quantify the electric field. You will be able to get equations for the electric field. Initially, we defined what is an electric field. Then we tried to picturize the electric field, or we got the different ways of representing the electric field. Now, our aim is to quantify or to get the equations for the electric field. Then the next section, we will be finding out how to find the electric field due to different charge distributions. Now, based on this definition for the flux, which is defined as Q divided by epsilon 0, I can redefine my Gauss's law as closed integral E dot ds is equal to Q by epsilon 0. Based on this equation, we will be able to, that is, my equation is closed integral over a surface. This is a surface integral. E dot ds is equal to q divided by epsilon 0. You will be able to find out what is the electric field. I want an equation for the electric field. I will be able to get the equation for the electric field using this using this law. We will be able to get the equation. And how to get that equation is, this surface we have to define what is the surface. The surface, for example, if I have a positive charge q is placed at somewhere, if I want to find the electric field to this point positive charge. And then if I want to apply this equation, I have to construct an imaginary Gaussian surface. This is what I meant by this surface S. I will be constructing like a fisherman trying to catch some fishes. I will be constructing an imaginary Gaussian surface around this positive charge. And if I want to find out the electric field at a point somewhere here, then that distance I will mark it as r. It can be anywhere. This imaginary Gaussian surface I can draw somewhere here, I can draw somewhere here, anywhere I will be able to draw the Gaussian surface. And then if I construct a Gaussian surface at a particular distance, then the electric field will be given by that particular distance, Therefore, I have to construct a Gaussian surface. Therefore, I have a positive charge here. This is my Gaussian surface. I want to find out what is the closed integral E dot ds. And on the surface, I will be constructing a small surface. On this whole surface, I will be constructing a small surface having the area, numerical area as ds. But this area, we have to note that this area is a vector quantity. Area is always a vector quantity. Actually, we will not be considering, for example, if you have a door in your house, that door will be having a direction. You will have to either move in the one side, we have to close it or open it, which means that that door has got a particular direction. If you are in a hostel and if you are waiting for the food, you have a plate there. You will have to put the plate in a particular direction that you get food there. Therefore, the direction of the plate will be like this. This is the direction in which we have to put the food there. Therefore, there will be a direction that is incorporated in a plate. In a glass, if you are taking tea, that glass will be having a particular direction. You cannot place the glass in this fashion. You will have to place the glass in such a way that you can have that tea inside the glass. Therefore, the glass or any surface or a plate or a door, any surface will be having a direction, and that direction will be given by, how can I find the direction for a surface? I will be dropping a perpendicular and then I will be giving a direction perpendicular and directed outwards. This is how you will be defining the direction for a surface. I will drop a perpendicular if I have a surface like this, I will drop a perpendicular and then I will give a direction in the outward direction. The direction of that surface will be always outward. Therefore, if you have a small surface here, the direction of this surface will be in this fashion. The direction of the electric field also will be in the same fashion. And that electric field is, I will be drawing a Gaussian surface in such a way that will be having a fixed distance at every point. And then automatically I will have a spherical surface around the positive charge. That is, if it is 5 centimeter, this will be 5 centimeter, 5 centimeter. Therefore, it guarantees that the electric field at every point around that positive charge is a constant one. Therefore, this E dot ds, my electric field will be a constant, and this is the vector scalar product. Therefore, I can have this E dot ds, I will be able to write that as E ds is equal to q by epsilon 0. I can write that as E ds cos theta equal to q divided by epsilon 0. And in my surface, I have this my elemental surface ds, my electric field is also along the same direction. Therefore, the angle between this E and ds will be 0 degree, or cos theta is equal to cos 0, which is 1. Therefore, this cos theta becomes 1. Therefore, the electric field is a constant. I can take that y, that is the way in which that I will be able to simplify my Gauss's law. Therefore, this can be taken outside, ds divided by q by epsilon 0. And this integral over the elemental surface. Elemental, if you have a cotton cloth or something like anything, any surface, you are actually making by knitting small surfaces. The knitting means it becomes a big cloth piece. Similarly, if you want to have a total area, you have to sum up all the small areas. Summing continuously is actually the mathematically, you call it as integration. Therefore, the integration of the surface will give you the surface area of a sphere, which is given by E into 4 pi r square equal to q divided by epsilon 0. Or you can say that E is equal to q divided by 4 pi epsilon 0 r square. Vectorially, I can write this as q divided by 4 pi epsilon 0 r square into unit vector r. This gives you the value of the electric field vectorially, and if I don't want the vector sign, I can cancel this and I can write the magnitude of the electric field will be equal to q divided by 4 pi epsilon 0 r square. This is how you will be able to quantify the electric field. Therefore, in my first session, what I had done is I had defined what is an electric field. Next, I constructed I imagined, the next step was to imagine how the electric field is around a positive charge, was positive or a negative charge, or around any charge distribution. And then by drawing lines of forces, I constructed the electric field. And finally, by using Gauss's law, I was able to quantify the electric field. We will stop this session now, and we will continue with finding out the electric field due to different charge distribution in the next session. Thank you.